So today we are presenting deep learning for anomaly detection in time series data. So this presentation contains topics like about time series, properties of time series data, industrial application of time series data, classical approaches and their challenges, use of deep learning methods in anomaly detection, and analysis and comparison of different deep learning methods for time series analysis. Okay, so let's start with about time series. Uh, So time series data is a kind of data where the data points are indexed in time order, and we can use this data to visualize the trend or to visualize the behavior of some machine, object, or any kind of entity. So, moving on. So anomaly detection is a process by which we detect unexpected items or events that can occur in the data which does not follow the proper and the expected trend. So anomalies can be classified into different types. They are broadly classified into point anomaly, contextual anomaly, and collective anomaly. So point anomaly is a kind of anomaly where where the issue occurs at a single data point. A single data point does not follow the trend and gets uh, out of the normal trend. Whereas in contextual anomaly, it occurs for a small period of time in a data section, and that data section lies within the normal range but does not follow the proper trend. And then there is collective anomaly. Collective anomaly refers to the set of data points that should be classified as anomaly because they gradually show a different pattern from normal data over time. Moving on, so these are the diagrams of different kinds of anomaly. This is point anomaly, this is a contextual anomaly, and this is a collective anomaly. Now we'll look into the properties of time series data. The first important property of time series data is temporality. A time series is generally considered to be a collection of observations indexed in time order, and so it is expected that every observation will depend on the previous observations. So this is the temporality property, that every observation depends on the previous observation, and thus there is a temporal dependence in the data. Then we come to dimensionality. Dimensionality refers to the number of individual data attributes that can be captured with each observation. These can be classified into two types: univariate and multivariate. In univariate, every data point is measured at a specific time and it is a real number. Uh, but in multivariate, the every data point is a collection of real valued observations, which are the attributes of the data, and so it can be seen as a multidimensional vector where each attribute is a univariate attribute. So thus it can be seen as a group of univariate time series data streams representing the state of the target system. So moving on, here comes non-stationarity. So non-stationarity is an important property in time series data. The time series is said to be stationary if the statistical properties do not change over time. So this means that if we translate the observations through a fixed amount of time, then the resultant time series data should not change. That's what it means. So this is conveyed in the equation. So and time series data might be non-stationary also in some cases, which like concept drift and change points. Uh, Here we are considering cases like seasonality, where seasonality is a periodic and recurring pattern caused due to weather conditions, holidays, marketing promotions, and other behavior that can occur in a system. Uh, then we come to concept drift. Concept drift is a property which introduces non-stationarity in the time series data. Uh, Basically, it leads to changes in the underlying statistical distribution of a data stream over time due to many different factors playing. Uh, then we come to change of points. In the manufacturing industry, the normal state of equipment often changes for several reasons, which can depend on various factors like how many workers are working, when the services are stopped, and when the machines are started running, what time of the day it is. and what is the condition of the raw material, and many different factors. So these factors can introduce a certain amount of non-stationarity in the data. Next we see noise. Noise is basically unwanted signals that get incorporated into the data, which basically has no relation to the data but are still present in the data and can hamper proper time series analysis in some cases. So in most of the cases, the noise that is captured with the data is generally small, and in such cases the noise can be safely ignored and we can proceed with our work. But in cases where the noise and the data cannot be separated properly, in that case it seriously affects the performance of models which detect anomaly in time series data. Moving on. So here we come to some of the industrial applications of time series data in different industries. We start with smart manufacturing. Smart manufacturing is a evolving domain, and many large industries have already shifted to smart manufacturing based techniques. Time series data can be very handy and useful in the context when used in the context of smart manufacturing. So some of the areas that it can be used are production equipment. Time series data can be used to study the behavior of the production equipment, the condition they are in, and it can be used to detect failures ahead of time and schedule maintenance. And all of this can be done without extensive domain knowledge because time series data does not rely on underlying domain knowledge. Then we can also use it in infrastructure facilities. It can be used to detect anomaly in some infrastructural devices like pumps that can be of use in manufacturing domain, and thus the uh, scheduling and maintenance can be done appropriately. Then it can be used in logistic automation system where there are autonomous guided vehicles that can be used in transportation of goods, and their functionality can be monitored and errors detected using this same time series analysis. Moving on, we have smart energy management. Smart energy management is also a growing sector, and time series analysis can prove helpful here also. Basically, three domains we are discussing here, like electric power. In electric power, time series can be used to detect anomalies in the data generated by power plant. This allows us to schedule prior maintenance. Then treated water. Water treatment and distribution is a huge industry, and there is also a high amount of risk of getting damages and unexpected behaviors. So we can detect these issues using time series data efficiently. Then manufactured gas. Manufactured gas is similar to treated water in the sense that there are also gas pipelines and distribution chains that can be vulnerable to damages and wear and tear. So time series also is useful in this domain. Moving on, we have cloud computing system. Cloud computing uh, is a very useful architecture that is used in across the internet, and basically cloud computing can use time series analysis for its performance and to improve the user experience. So in cloud computing, the server machine can collect the data, uh, can collect the time series metrics like the processor load, network usage, memory status, and different kinds of data that can be made available by the administrator and can be fed to a time series data model, and anomalies or general trends can be figured out. Also, it can be used in network and framework. By getting the data of network, we can understand that what is the trend of network usage, what time the network grows exponentially, what time the network traffic stays low. So in by this analysis we can figure out the best way to design a network and distributed systems. Also in cyber security, in addition to physical threats, there are also malicious cyber attacks that can become critical for reliability and security of cloud systems. Uh, Time series analysis can also detect such attacks if they have been executed on any cloud computing architecture. Moving on, so here we Here is the structural health monitoring. This is also a very important domain that can use time series analysis. Basically, it studies the damage and corrosion that can occur on structural uh, establishments like bridges, roads, buildings, etc. So structural health monitoring basically detects the loads and responses and identifies the abnormal behaviors of these structures, and basically it can predict the upcoming damages or upcoming maintenance if they are required, and what is the expected lifespan of such structures. Moving on, now we'll be looking over the existing classical approaches uh, that are designed for time series analysis and anomaly detection. So there are five classical approaches, starting with the first, time frequency domain analysis. Time series data can be analyzed in the time domain using the width and height of measured thresholds. Okay, so time and frequency domain analysis can be done by measuring the width and height of threshold, and also the another and the more popular way is to use a Fourier transform over the data to separate the given signal into corresponding simpler and sine and cosine waves. After doing Fourier transform, we can get the frequencies of all the data, all the different signals that are present in the data in a sorted order, and then we can invert the frequencies to get the periods of the data. So this is one of the most common and well-known technique for time series analysis. Uh, Moving on to statistical model. Statistical models are old and very useful technique for analyzing time series data. Here, while looking at the data, we calculate many statistical measures and variables like mean, median, variance, quantile, kurtosis, skewness, and many more. So with these generated information, we can test that any new data, whether they fit in the existing distribution or not, and thus we can predict whether there is some anomaly or not. Okay, moving on to distance-based model. Distance-based model is basically it is an algorithm that measures explicitly the distance between two sequences to quantify the similarity between the two. The most simplest approach is to use the Euclidean distance, where we basically just calculate the distance by using a simple x minus y square. So this is a very simple method, but we can use more efficient methods as well, like dynamic time warping. It is a popular distance measurement tool which allows nonlinear alignment between two sequences as well. So for this, we create a cost matrix using dynamic programming algorithm, and basically we use a top-down DP approach to calculate the optimal path, choosing the previous point to the lowest cumulative distance. So basically from here we are choosing the points with the lowest distance, and we are updating and we are calculating the distance of the next points. Finally, after the DP is completed, we are calculating the final distance by summing the values of WK. Moving on, here we have predictive model. Predictive models are basically used to forecast future state based on past and current state. Basically, the most common algorithm in predictive model is the autoregressive integrated moving average. ARIMA model, it is also known as ARIMA model, and it is composed of three parts: a mu, and then ARP and MAQ. So mu is a constant, while ARP is the autoregressive part, and autoregressive just means that it is basically the sum, weighted sum of the values that occurred previously in the data. So all the values from uh, t minus p to t minus 1 are used in this autoregressive section, and it basically just calculates the weighted sum with some weights, and this is the ARP, and the MAQ is the moving average part. Basically, the moving average ensures that we are also calculating the expected error by calculating the moving average of all the previous errors. So moving average model computes the weighted sum of lagged prediction errors, and it is formulated as this. So basically this is a moving average of all the prediction errors that were encountered previously. So this uh, also uses the integrated. Basically integrated here indicates that the time series uses differences. So basically which means that the data point at time step t is xt minus xt minus 1. So this is the meaning of the word integrated in the ARIMA term. So basically this is what a ARIMA model looks like. Moving on, so now we'll be discussing some challenges that can be faced while doing time series data using classical methods. Uh, the first challenge is the lack of labels. The scarcity of failure modes makes collecting enough label training time and resource intensive. So basically the problem with time series data is that there are very few data samples that exist that actually shows anomaly within the time series data, because failures are very much uncommon in modern day industrial setting. So this creates the data collection difficult, and also if we have, even if we have data, the data has a huge amount of class imbalance which hampers the training. And also the second point is the complexity of the data. Time series data can have a huge number of dimension, and basically can span over multiple uh, so huge number of attributes. So traditional approaches basically they get a performance drop due to the curse of dimensionality, and also most of the traditional models cannot mm, capture complex correlations between different variables, and so these cannot be used for highly complex data that have multiple nonlinear correlations between multiple variables. So this is one of the these are two of the major issues that are faced during time series analysis with anomaly detection.
So till the last section we have seen some of the classical methods for anomaly detection, but those methods have many drawbacks. So in this section we are going to see some deep learning based methods for the anomaly detection. In this section, we are going to analyze these methods from three perspectives: how they define intercorrelation between the variables, how they model the temporal context information, and how they define the anomaly scores or thresholds. So, first, beginning with the intercorrelation between the variables, there can be various ways like dimensional reduction, 2D matrix, and graph. So first of all, let's see what is dimensional reduction. In dimensional reduction, we need some significant factors out of a large scale system. For that, we can use ECA or SVD as linear algebra based approaches, or if we want to use deep learning based approach, then we can use autoencoders. These provide important features, but with a drawback that detecting the cause of the anomaly becomes difficult after dimensional reduction. Moving on to the 2D matrix. 2D matrix directly captures the similarity and the relative scale among the variables. It is robust and time efficient. Uh, like here we see there are two expressions which we can use to model the 2D matrix. On one hand, if the phase of the entire variable suddenly rises or falls due to an unexpected event, the first equation can result better than the second one. On the other hand, when the overall phase changes by a concept drift or a change point, the second equation diminishes this event as normal, while the first equation flags it as an unnecessary alarm. Moving on to the graph based methods. A graph can define an explicit topological structure and learn the causal relationship among the individual variables. So there we can create a directed graph where V is the set of vertex and E is the set of edges, and generally using a graph we can calculate the attention scores, like with this here yi denotes the feature representation of the node I, and sigma corresponds to the sigmoid activation, and alpha ij is the attention score, which measures the influence of the node j to the node I, and vj to the feature vector of node j. Moving on, let's discuss about how we model the temporal context. There are multiple methods like RNN, CNN, hybrid methods, and attention mechanisms. So let's first discuss about RNN. RNN based approaches are generally used for anomaly detection in two ways. One way is to predict the future values and then compare them with the predefined thresholds or the observed values, and the other way is to construct a autoencoder or VAE to restore the observed value and evaluate the discrepancy between the reconstructed value and the observed one. Moving on, let's see about the CNN. CNN models learn the parameter in segmented time series. So one of its drawback is that uh, it is not easy that we can comprehend behaviors over a long period of time. So we move from the CNN to TCN. In TCN, the convolution is in the model are usual, meaning they ensure no information leakage from the future to the past. Second, it can take a sequence of any length, just as we discussed in the RNN. And third, it can look quite far into the past and forecast the future. Uh, Moving on to the hybrid methods. In hybrid methods, we use generally LSTM based methods. In LSTM, we replace the dot products with the convolutional operators, and all gates and states in the cell are reshaped to a 3D tensor. Uh, and then it is able to model the context very easily. Uh, One more method is the attention mechanism. The attention mechanism was initially built as an auxiliary tool, which are used for the NLP tasks. So slowly, the attention mechanism developed, and many transformers and bidirectional encoder representation transformers, the BERT, are introduced. And by paying attention to the input weights that contribute more to the output, the attention based models can capture very long range dependence with a relative importance of each of the data points. Moving on, let's discuss the anomaly criteria. So the anomaly can be characterized by its reconstruction error, prediction error, or dissimilarities. So talking about the reconstruction error, as we have discussed already, the models like autoencoder and GAN transformers use reconstruction error as anomaly scores. The autoencoder based models reconstruct the input data by extracting features from them, while the VAE based models such as estimate the data distribution and generate samples from it, which are very similar to the input data. Models use different training schemes and objective functions. They calculate anomaly scores similarity. They reconstruct or generate data analogous to the input data and measures the residual between the input and the generated data. Moving on to the prediction error, there are two ways to derive anomaly scores from the prediction error. One applies a binary label based on probability and data point being classified as normal. The prediction error indicates whether the expected label matches to the ground truth or not. The other approach is to predict the expected value for the next future steps, and then move to the next step and check whether the prediction is correct or not. The second one is more practical than the first one, as labels are insufficient in the real world data. Moving on to the dissimilarity based one measure how far the value derived by the model exists from the distribution or cluster of the accumulated data. We use various methods like Manhattan distance, Euclidean distance, Chebyshev distance, cosine correlation to measure the dissimilarity between the data. The similarity obtained from the model is subtracted from one to obtain the anomaly score. Moving on to the analysis and comparison section. In this section, we are going to compare different kinds of model based on their accuracies and the other evaluation metrics. So before moving on to the actual comparison, let's discuss what the data sets we have used for this comparison. So the data set that we are going to see are SWAT dataset, which is secure water treatment. It is a multivariate time series dataset collected over 11 days from a water treatment test bed, a small scale cyber physician system that last 4 days of data contains 36 attacks that we have to predict. Water distribution VADI dataset, multivariate time series data from water distribution pipelines collected over 16 days. Each series include various network traffic sensors and actuators measurings. Mars Science Laboratory Rover MSL dataset, which is multivariate time series data again recorded from the Mars Science Laboratory Rover. So in this table, we can see what are the dimensions of these data sets, the number of training examples, testing examples, and the anomaly rate. Moving on to the evaluation metrics, we will use precision, recall, and F1 score as our evaluation metrics. So here are different hyperparameters that are used in the different kind of model for training and testing purposes. And in this slide there are results of the various model. The data which are colored dark black are the best out of other. These graphs shows how the results perform on SWAT and MSL dataset. These graphs are basically based on the RNN based transformer methods, and these are on SWAT, MSL, and WADI dataset by using different models. So here is the comparison between the different best performing models on their precision, recall, and F1 score. Results and analysis. So we have seen many state-of-the-art multivariate time series anomaly detection models. Few are based on the autoencoder like DAGMM, MSCRED, Omni Anomaly. Some are based on VAEs like LSTM VAE and USAT, GAN based model like MADGAN, RNN based model like THOC, transformer based models like GTA, and CNN based models like GTA and CDN. So each of these methods prioritize a different metric as the author chooses to prefer the thresholds depending on their goals. We will pick F1 score as the baseline to sort the method for the SWAT dataset. So first of all, let's see how this model performs on modeling the temporal context and or temporal dependencies. So the RNN based model shows better performance compared to the DAGMM model. The average F1 scores of the RNN based models on SWAT and MSL datasets are 1.8% and 14.9% higher than those of the autoencoder based DAGMM model. Most of the RNN based methods outperform the AE based DAGMM model, but an exception occurs at the LSTM VAE on MSL dataset. The main reason for this phenomena is due to the latent variables, the better temporal dependency or the context better modeling of the temporal dependency that the LSTM VAE can do. Moving on to the parallel processing for long sequences. So one drawback for the RNN is that it restricts the parallelization because it computes the output sequentially. Meanwhile, the transformer takes the sequence at all. So parallel processing and computations are feasible in the transformer based approaches. This property is significant to sequence modeling because longer sequence can provide more information. Consequently, compared to DAGMM and GTA that aims to adopt transformer achieves over 6.898% and 30.01% improvement in terms of the best F1 scores on SWAT and MSL dataset respectively. Moving on to the dimensions of dataset, we see that the overall performance of the best F1 scores on the varied dataset are significantly lower to compare to the other dataset, SWAT and MSL. Uh, Expect for the GNN based of the varied dataset is 112, that is double the SWAT and the MSL dataset, and due to this, few models perform a little worse in varied dataset than SWAT and MSL. Moving on to the intercorrelation between the attributes, the SWAT and the WADI provides network traffic measurement from sensors and actuators under several processes. These attributes are not entirely independent of each other, and thus there exists some intercorrelation between the attributes. As a result, we observe that the graph structure learning with attention mechanism like GDN is more effective on these types of dataset where the elements are strongly correlated with each other. So that's all. Thank you. In case of any doubts, you can contact us. Uh, Thank you.